Hello and welcome to this video. In this video, I'm going to solve the last three exercises of chapter 1. Okay, let us start with exercise number 11. In this exercise, we have to prove that r star, which is r without 0, the complement of 0, and the complement of the integers, and the complement of the non-negative integers are all dense in R, which means that their closures is equal to R. So let us start with the first example. So R star. I will present three ways of proving that A bar is R. The closure of A is R. Okay, now A bar is always a set between A and the space in which it lives, which is R in this case. So we have a closed set which is between R without 0 and R. Okay, these two sets, R star and R, differ only by 1 point. So we have two possibilities. The set in between is either the first one or the second one. There are no other cases. Okay, now it cannot be the closure of R star, it cannot be equal to R star. Why? Because R star is not closed, right? So this first possibility cannot hold because R star is not closed. Why is it's not closed? Because, for example, we can take a sequence, for example, 1 over n in R star, converging to 0, but 0 is outside R star, right? So therefore, we are just left with the second possibility. So the closure of R star is R, actually. We did something similar in the beginning, in the lectures, actually. Okay. Now, second way, we use proposition 1.6. So we want to prove that A bar is R. So how do we prove that? Double inclusion. Okay, now A bar is always in R. That's true because we live in R, in this chapter at least. And we have to prove that the reversed inclusion, R is contained in A bar. How do I prove that? I take an arbitrary point X in R and prove that's in A bar. How do I prove that X is in A bar? I use proposition 1.6, which tells me that every neighborhood of X meets A. If this is true, then X belongs to A bar. So consider an arbitrary point X in R and an arbitrary open neighborhood U of X. Now, the set 0 is not open, so U cannot be equal to 0, right? Cannot be contained. Actually, we observed that 0 cannot contain any open set except the empty set, right? So it means that there is a point, let us say Y in U, but different from 0, not in 0. So there is a point in the intersection of U and R star. So the intersection, so this neighborhood U of X meets A, or R without 0. Therefore, by proposition 1.6, X belongs to the closure of R without 0. But since X was arbitrary, we have proved that the whole line R is contained in R star, in R without 0, in the closure of R without 0. And of course, we also observed that R star is contained in R, so we have a double inclusion, and therefore we have equality. Okay, third way, we also use proposition 1.6, but with sequences this time. Okay, what do we have to prove? We have to prove that every element in X is the limit of a sequence in A, in R star. Okay, it's easy. If X is different from 0, take the constant sequence, xn equal X. So we have two cases. If X is in R, so either X is 0 or X is different from 0. If X is different from 0, it's easy. Take the constant sequence, xn equal X. Then, of course, xn converges to X. And xn is a sequence in R star. If X is 0, take the sequence 1 over n. This sequence is in R star and also converges to X. So in both cases, in all cases, we can construct a sequence in R star converging to X. And by proposition 1.6, X belongs to the closure of R star. And therefore, we have a double inclusion, right? We have R in R star bar and R star bar is in R. Therefore, we have equality. Okay, this concludes the first item, R star. Okay? Now, R without Z, we will also do a parallel of these three methods. You choose the one you like or you understand the best. Okay, so consider the case of the complement of the integers, r without z. Okay, so if we want to follow the same first way as in the previous example, the closure of r without z is a set between r without z and r, right? Okay, now, but here the situation is a little bit more complicated because we are removing from R an infinite set, not just a point. Okay, now, so R without Z is obtained by adding to R without Z some set or some points, right? How do you obtain R without Z bar? We add to R without Z some points. So let F be this set that we add to R without Z in order to obtain the closure. Okay, if you like, F is just the difference. F, you can take F as being the closure of A minus A, if you like. Okay, but now, what is R without Z union F? This can be written as R without Z without F. It's easy. It's just an easy exercise in set theory. Okay, you can easily prove that these two sets are equal. So actually, I remove Z and then I add some points. Okay, so it's like adding some points, removing some points from Z, right? So, okay. Now, since this set R without Z without F is the closure of A, so it's a closed set. So its complement, which is Z minus F or Z without F, is open, right? Fine. But actually, the only possibility is that this is empty. It cannot be not empty. Why? Because if an open set is not empty, then it contains a whole interval, right? By definition, it contains a non-trivial interval. Okay, but a non-trivial interval is uncountable, right? So Z without F would contain an uncountable set, and therefore it would be itself uncountable. But it's countable by construction, right? Because it's a subset of Z. Z is countable. So Z minus F, which is a subset of Z, is also countable, right? And that's it. So the claim is proved. If F is Z minus F is empty, then F equals Z. And we get just A bar equal to R, because this is Z minus F is empty. So R without the empty set is just R. Okay. This is the first way. Second way, similar to the previous one. So we take an arbitrary point X in R, and we consider an arbitrary open neighborhood. So I told you that you can always consider take your neighborhoods to be open, right? Because if they are not open, you can take smaller ones which are open. Okay. Now, once again, Z cannot contain a non-trivial open set. Okay, because a non-trivial open set contains an interval. And an interval cannot be contained in the integers because it contains, for example, irrational numbers. We observed this before. So Z, actually, when we prove that the interior of Z is empty, okay, we use this fact. Okay, so if U is not contained in Z, then it means that U meets the complement of Z as before. And so by proposition 1.6, X belongs to the closure, and therefore we have a double inclusion, and so on. Okay, so it's completely similar. Just to replace the singleton zero by Z. Okay, so this makes maybe easier actually. And third way, same thing, completely parallel to the previous example. Okay, we take an arbitrary point X in R and we find a sequence in R without Z converging to R. Okay, we distinguish between two cases. If X is not in Z, take the constant sequence as before. So it's a sequence in the complement of Z because, okay, Xn equal X and X is not in Z. So the sequence is not in Z and converges to X. If, however, X is an integer, say M, just take the sequence, perturb M by a small amount, M plus 1 over N, or any sequence that converges to 0 and is less than 1, right? So xn now is a sequence. So if m is in z, m plus 1 over 2n, which is at most 1/2, if n equal 1. So it's 1/2, one we start with 1/2, 1 over 4, 1 over 6, 1 over 8, etc. Okay, so this quantity m plus 1 over 2n is not an integer. Okay, it's an integer plus something very small. So xn is a sequence in R without z, and of course converges to x. Here m is fixed and n is variable. Okay, so in both cases we found a sequence in R without z converging to x, and therefore by proposition 1.6 x belongs to the closure, and as before the closure is R because we have a double inclusion. Okay, so completely parallel. And the last example is completely similar to the second one. Okay, just you can do it by yourself. Use the method that you like. Okay. So this concludes exercise. So here it should be this z here should be like this z here. Okay. The integers. So this concludes exercise 11. The next exercise, also about density. Okay, first question. We have to prove that the floor function of 2 to the n times x over 2n as n tends to infinity is x. The limit is x. Okay, and deduce the density of two sets. This is easy, actually. We go back to the definition. The number is always between any number is actually bigger or equal than its floor function and less than its floor function plus 1. So I just rewrote these two inequalities in a different way, right? So we can say that the floor function of a number is between the number minus 1 and the number itself. Yeah, but the inequalities are reversed actually. So we have less or equal here and strictly bigger here, right? So this is just the definition of the floor function, but written in a slightly different way. And now we are done because you just divide by 2n. We get that floor function of 2nx over 2n is between x minus 1 over 2n and x. And we are done because 1 over 2n converges to 0, so the left-hand side converges to x, and the right-hand side is constant, so it converges to x. By the sandwich theorem, what is in between also converges to x. Okay. The sandwich theorem is known in French as théorème de gendarme. Okay. So this concludes the first question. Okay, we have to deduce that the set of all rational numbers of the form m over 2n is dense in R. Where, okay, so these are just particular. So actually, it's not trivial because this is not the whole rational number. It's a subset of the rational numbers, right? Okay, so it's a smaller subset. So we cannot deduce the density of this set from the density of the rational numbers. But we can deduce the density of the rational numbers from the density of the set because the Q is bigger. Okay, so same idea. We take an element x in R and we find a sequence in the set A. I call it A. This subset of the rational numbers, I call it A. I want to find a sequence of A converging to x. So it's very easy because this follows from the previous question. The sequence floor function of 2nx over 2n belongs to A. Why? Because it's the form of an integer, okay, a relative integer, over 2 to the n, right, for any n. Right, and that's it. By the previous question, this sequence converges to x. So we found a sequence in A converging to x. By proposition 1.6, x belongs to A bar. So as usual, A bar is equal to R here because we have a double inclusion. Okay. Second question, we have to prove we have a smaller set now because now we restrict m to be less or equal than to n. So the numbers, so this is, so we let us call it B, this set actually now. Okay, so we have the set B here, call it B. It's a subset of A actually, but it's a subset of 0, 1, not a subset of R. So it cannot be dense in R actually, but it's dense in the interval 0, 1. Okay, so once again, this idea is similar, but it had to be a little bit modified. So let M be the floor function of 2nx. Okay. Then, since x is positive, bigger or equal than 0, 2nx is bigger or equal than 0. So the floor function is bigger or equal than 0. So the first observation is that M is non-negative. The second observation is that 2nx, so M is less than 2nx. Right? So when I divide by 2n, I get M over 2n less than x. Why? Because M is the floor function of 2nx. Right? But x is less than 1, so actually M over 2n is less than 1. So the sequence defined by M over 2n, if you like, belongs to the set B and converges to x by question A. Right? So once again, x belongs to B bar, and so B bar is equal to 0, 1. Okay, so this concludes exercise 12. Last exercise, also about the density of some special subset of R, the set of all elements of all real numbers of the form m minus len of n. Len is the natural logarithm here. Okay, so it's the inverse of the exponential. Okay, now this exercise, I confess that it's a little bit tricky, so I don't expect from you to solve it on your own. Okay, but it's interesting. So one way, we also use proposition 1.6. We have to prove that every neighborhood of, so we take an element x in R, and we prove that every neighborhood of x meets A. But we saw that this is equivalent to saying that the interval x minus epsilon, x plus epsilon meets A. Right? Same thing, because x minus epsilon, x plus epsilon, if epsilon is given, is a neighborhood of x. And any neighborhood contains such an interval of this form. So it's enough to prove that x minus epsilon, x plus epsilon meets A at a certain point of the form m minus len n. Okay? Or if you like, m minus len n minus x is between minus epsilon and epsilon. Same thing. So these two conditions are equivalent. Just if you add x, you get x minus epsilon, x plus epsilon. So same thing. Okay, so this is our target here. And actually, we will prove something a little bit more. We can take m minus len minus x to be positive if you like. So in just one part of the interval. But it's not important. Okay. So we have to choose two integers, m and n, so that this condition is satisfied. Okay. Epsilon is given here. So first thing we do is we take m sufficiently large, an integer m sufficiently large, so that it's bigger than x plus len of 1 plus 1 over epsilon. And you'll understand in a moment why did I choose this condition. Okay? Why did I take len of 1 plus 1 over epsilon, not something else? Okay. This is the tricky part, actually. And we know that such m exists by the Archimedean property of R, and I can take actually m to be an integer, a non-negative integer, right? So I can take m in n. So this is my first choice of m. Now, for n, I don't have many choices. I have to be, okay. So the idea is actually what? I want m minus len n, or m minus x, to be close to len n. Okay? But big enough. If we take n to be the floor function of e to the m minus x, then what? Then, by definition of the floor function, the exponential of m minus x is between n and n plus 1, right? This is the definition of the floor function. And so when I take the logarithm, because the logarithm is strictly increasing, so I get len of n is less than or equal than m minus x, and this is less than len of n plus 1. Okay? Therefore, when I subtract len n from, so m minus x minus len of n will be greater or equal than, bigger or equal than 0. This is the sort of thing. And if I consider this inequality, second one, and subtract len of n, I get m minus len n minus x less than len of n plus 1 minus len of. Okay? And now we are almost done, because we can write this len of n plus 1 minus by the fundamental property of the logarithms. The difference is just the len of the ratio, n plus 1 over n, which can be written as len of 1 plus 1 over n. But we know that len of 1 plus t is less than t for t positive, right? Which means that, if you like, the logarithm is below, it's concave, so it's below its tangent, right? So I hope that you know that len of 1 plus t is less than t for t positive. And now we are almost done, because if I go back to my choice of m here, we get m minus x bigger than the logarithm of 1 plus 1 over epsilon. So when I take the exponential, because the exponential is strictly increasing, I get e to the m minus x is bigger than 1 plus 1 over epsilon. Right? Now, we use this inequality, this one. E to the m minus x is less than n plus 1. So when I subtract 1, I get n, actually strictly bigger, it should be strictly bigger here, but it's not the big deal. It's strictly bigger. So n is strictly bigger than e to the minus mx minus 1 from this inequality. And e to the m minus x minus 1 is bigger than 1 over epsilon. So I get n bigger than 1 over epsilon. And so 1 over n is less than epsilon. So the difference m minus len n minus x is less than epsilon. And so we have proved that m minus len n minus x is between 0 and epsilon. Okay, so in particular it's here. Okay, so that's it. This proves the density of my set A. Okay, so now we finished the exercises officially. We finished officially the exercise of chapter 1. But I have something to add to chapter 1 actually. I have 3 appendices to this chapter. In the next video, I will talk about subgroups of R+, or additive subgroups of R. Okay? Thank you for your attention.